And from current slide. Okay. And we may even turn on the projector today. I was thinking I was going to be talking to myself, so I don't usually turn on the projector for that. But I forgot to turn it on when you came in. All right, we were on in Chapter 2, Section 2.1. And by the way, I know you were disappointed I didn't have your test ready. It's so close to being ready. I've got everything typed in, but it's not spaced correctly, and I haven't gone back to check it again. So hopefully, if not by the end of the day today, possibly I'll have a little time on Thursday, tomorrow. I'm going to be on Birmingham campus on Friday, so I may not. So I don't know. Hopefully I'll have it ready for you by next week. But on Monday, but not today. Yeah, you got something to keep you busy. I'll keep you off the streets. Okay. All right, we were in Chapter 2, 2.1, which is first order differential equations, or Chapter 2 is first order differential equations. 2.1 is solution curves without a solution. Okay, that's drawing the curves, and here's the Silva. I know you said you would be back, and I believed you. Hopefully Nigel will be back too. And maybe even Matt will come in. All right. Now, I got to fretting on this and thought, why are we going over this? Solution curves without a solution. Yeah, it's sort of interesting and stuff, but it's, well, we'll just go on with it. I'm really of the opinion, let's move on through this and get to the real, what I consider differential equations. This is having to do with it, but let's go from here. Okay. What we were doing last time, example 5, we had started on that, and it says, y of x, well, let me get my pen set up. Okay. Hopefully, yeah. Y of x is equal to 1 minus 1 over x plus c, okay, is a one-parameter family of solutions of the differential equation. Now, this differential equation is this one. dy dx is equal to, hey, here they come, more and more, that's what you see, Nigel's here, okay. My work-study student this term took differential equations last term. I think there were officially supposed to be 5 people in the class. And our class, really now that we've added Antonisha and Charles, we're up to 1, 2, 3, 4, 5, 6. But with the 5, so many of the classes, he was the only one here. He felt like it was a one-on-one tutoring, I think. And when he heard that more than one was showing up this term, he was a little jealous. Okay, so anyway, Matt's here. So y'all are doing real good about coming. Much better than the team did last time. All right. We're doing, this is continuing example 5 on page 41. The differential equation was dy dx is equal to y minus 1 squared. Okay. Now, it says that this is a solution to it. Okay? And it says you can go back to exercise set 2.2 and see problem 4. And that is, okay? Well, let's see. Is indeed that the case? Well, let's see. dy dx here would be what? The 1 doesn't contribute anything. You'd have a let me rewrite this ever so slightly. I'm sorry, 1 minus x plus c to the minus 1, right? That's the same y. I'm just writing it in exponential form rather than fractional form. Okay? You buy that? Okay? Now, let's take a derivative of that. What would you get? 1 doesn't contribute anything. Take the derivative of this. Second? Okay, yeah, this is a minus from there, but you have a minus 1 here. So that would be positive. X plus c to the minus 2. Is that what you said? Yeah, okay. Which would be 1 over x plus c squared, right? And, okay, well, that doesn't quite jive with the above, but let's see. Y is this, so this would be 1 minus 1 over x plus c, right? That's what y is. Minus 1, well, they go away, squared. And yes, that is the same thing as this. So yes, that does match, okay? Took a little bit of effort, but that does work. All right, now, a given initial condition determines the value for C. For initial condition, let's just say that y of 0 is equal to 1. No, I'm sorry, equal to negative 1. Okay? No, I'm sorry. There it is, yeah. Let's just say, for initial conditions, let's just say y of 0 is equal to negative 1. This is weird notation the book is using. Really shorthand. I understand what they're meaning. No, I don't understand what they're meaning. Here's what they've written here. Y of 0 is equal to negative 1 less than 1. Okay. At first I thought they were meaning by that is equal to negative 1 for any y's, for any x's less than 1. And that makes sense. Until I read the next statement here, and it said y of 0 is equal to 2 greater than 1. That makes no sense any way I read it. Okay? Number 1, 2 can't be greater than 1, so that makes no sense. But while I was reading this one was is equal to 2 for all x's greater than 1. But guess what? 0 isn't greater than 1, so that doesn't make any sense. I don't think that's what they meant, okay? In fact, I'm not sure what they mean, okay? Oh, got it. Okay. I think that's supposed to be a minus here. This is a less, no. I still think they've got it wrong. But we'll see. The statement, that is a confusing statement. I think I sort of see what they're saying, but it's still not right, okay? So, let's take the first one. Y of 0 is equal to minus 1, okay? Well, here is our function, okay? And let's do y of 0, okay? So, y of 0 is equal to 1 minus 1 over c, right? Because when x is 0, y is, and this is equal to 1, so this should be 1, right? Y of 0 is equal to 1. Oh, negative 1, sorry. When x is equal to 0, okay? So that would be less. How I'm going to do this is add a 1 over c. Well, let's see. I think the easier thing to do, I started to do it one way, I think I'll do it. Okay. I think the easiest thing to do here, or at least an easy thing to do, multiply both sides of the equation, every term on both sides by c. So this will be multiplied by c, this is multiplied by c. C, not raised to c, but that would be c minus 1 is equal to minus c, right? Let's add a c to both sides, and you get 2c, and subtract and add 1 to both sides. 2c is equal to 1, c is equal to 1/2. Okay. Now, maybe what they were meaning here, this is good for c's less than 1. I don't know for sure if that's what they meant, but that could be what they meant. Okay? Not x is less than 1, okay? Or certainly not negative 1 less than 1, it always is. But for c's less than 1, and 1/2 would be less than 1. Okay? Do all of you have books or e-books or something? Okay, everybody got one? Oh, you don't yet? Okay. Okay, I'm going to erase some of the stuff here just because we've already done it and hopefully we don't have to redo it. But I'm going to erase this. That's our differential equation that was being satisfied here. Okay. Now, they draw the thing here. Oh, and by the way, that gives us our solution of y of x is equal to 1 minus 1 over x plus 1/2. Okay? Now, looking at that, I think you can see you have a, do you think you see a vertical asymptote anywhere in there? Not at 1. What in that equation can you never have? Negative 1/2. So negative 1/2, if that's negative 1, negative 1/2 is here. I think I like to draw vertical asymptotes in red so you're certain to see. You can't go there, folks. Okay? And by the way, you can do a y-intercept pretty easily here. Say x equal to 0. Let me put my pen back to black. Okay. When x is equal to 0, you have 1 minus 1 over 1/2. 1 over 1/2 is 2, right? 1 minus 2 is negative 1. So when x is 0, you're down here at negative 1. Okay. Now, another thing that I would note here, when x gets extraordinarily large, what is your y going to? Well, this term right here is going to 0, right? The second term. So you're going to 1. So y is equal to 1, maybe I should do this in red too, is a horizontal asymptote. Okay, now you can touch across that one, you just can't touch across a vertical asymptote. Okay, now if your y-intercept is there, then this side of the curve is going to do something like this, and I'll almost guarantee you that this side of the curve is going to be like that. If you want to check to make sure, let's just plug in a value, like x equal 1. Well, go back to your original equation here. You have y of 1 would be equal to 1 minus 1 over x plus 1. No, 1 plus 1/2, sorry. 1 plus 1/2. 1 plus 1/2 is 3/2. And 1 over 3/2 is 2/3, right? And 1 minus 2/3 would be 1/3. I missed that one, didn't I? I must be doing something wrong. Let me go back and try that one more time. When x equal 1, that would be 1 minus 1 over 1 plus 1/2, that would be 3/2. 1 over 3/2 is 2/3. Unless I'm doing something really, really wrong, they've got theirs in the wrong place. Seems like it should be down here. And that doesn't look like that would be right. So is there anything else? Okay, now I'm beginning to see what their statements are meaning. I can see it when I look at the graph. What this is meaning, this is when y is less than 1, okay, which is a weird way to do it. I'm sorry, when y is less than 1, and this is when y is greater than 1, okay. Strange but true, okay. Well, then y less than 1, the red part wouldn't make any sense. Because that's not your function. So that's why it's not making any sense on the graph. So this is, okay. All right. Sorry, this is a really bizarre kind of setup, especially the way they write the problem. This one doesn't make sense. This is good. For any y's that are negative, this is what the function is. In fact, I would say this is not the case. No, y less than 1. I'm sorry, y less than 1, you're okay. Y less than 1, you're all right for these values to be in there. Y less than 1, not y less than 0, y less than 1. Okay, so that part of the curve. But then they give you this part, that the initial condition for y is greater than 1 is a different initial condition. It's equal to 2. I know it's written here, I just can't see it. Yeah, y of 0 is equal to 2 for any y's greater than 1. Okay? So in that case, we have our same setup here, and I'm going to use the same axes if it's okay, because I don't have room to do another one. So let's get rid of this. The y is okay, leaving the horizontal axis there, okay, but I'm going to change my vertical, okay. Yuck. Okay. If I can ever get this back. Okay. All right. So we have a different initial condition for y is greater than 1, above the red line. And what you do there is it equal to 2. So go to your equation, y of 0 is equal to 1 minus 1 over x plus c, and now it's equal to 2. Okay, so forget y0 for now. Oh, that's just c because x is 0. Okay, so now we're going to multiply both sides of the equation by 2 again, by c again. That would give you c minus 1 is equal to 2. What does that give you? Not that hard. Oh, wait. It's 2c. Sorry about that. Write the equation right, and it may not be. It might be a little harder. Okay, what would this be then? Subtract c from both sides, and you get c is equal to -1. Okay, so now your equation is y of x is equal to 1 minus 1 over x minus 1. So again, you have, now your vertical asymptote is over here at 1. Okay, that's why I erased it before. I knew that was going to change. So your vertical asymptote is here. And it's real easy here to plug in x equals 0. And that gives you y is equal to 1. Well, you should already know that answer. It's equal to 2. And that sure enough gives you 2. Y minus a minus 1, which is 2. So let me go back to black here. And this would, thought I went back to black. There we go. Okay, so there is your y-intercept here. Okay, for any y is greater than 1. So this puts you going up like this. So there is your function for y's greater than 1. The other one was y's less than 1. Okay, so we won't even put anything down here because it's immaterial what that is. Okay, and they draw a curve down in the lower quadrant here. I'll be willing to give it a shot. Let's take x equal 2 and see what you get. That'd be 1 minus 1 over 1. That would be 0. So 2, 0. Yeah, that looks like that would be down here. So yeah, that curve would be here. So that one makes sense. The last one, I couldn't get that answer that they got at all. Okay. But yeah, 2 at 0. So anyway, both of these are increasing functions. We saw that earlier, and we've got what those two are. So basically it breaks down to y of x is equal to 1 minus, okay, this was our first equation here, and where is that good? That's only good for x's from -1/2, which is where that one started, -1/2 to infinity, greater than -1/2. And this function here, this one here, is good for x's from infinity up to 1. Now, I want to give a big time out here. That, in effect, to me, doesn't make a lot of sense, okay? Because here's what they're saying, and you can read it in the book. It's right there. They say this one's good for -1/2 less than x less than infinity. And they say this one up here is good for -infinity less than x is less than 1. That's what they say in the book, right? Okay. Here's where my problem comes in. If I can find where I just wrote that. Notice here, from -1 to 1, these are -1/2 to 1, that's included here. But -1/2 to 1 is also included up there. So you've got overlapping domains with two different functions. How in the world can that be true? So this, to me, was a rather ill-posed problem. And that's what's been confusing me from the beginning on it. What in the world are they meaning by this? Now, maybe there's some legitimate answer to that, but frankly, it all depends on what value the y is. That's what they were telling us before. For y is greater than 1, you use 1, less than 1, you use other. But then, in my mind, these descriptions here don't make sense. Put your y's in there, don't put the x's in, okay? But that's just my little thing. Okay. They have a little blurb at the bottom, attractors and repellers, okay? Suppose that your y of x is a non-constant solution of an autonomous differential equation. Remember what your autonomous differential equations are. If you go back to, I think they mean equation 2. They say equation 1. And equation 1 is way back here. Yeah, okay. It's the same. Okay. No, it isn't. Okay. Autonomous has no x dependence, whereas 1 does. So I think they meant given in 2, not 1. And that C is a critical point of the differential equation. Okay? There are basically three types of behavior that y can exhibit near C. Okay? Now, I'm going to clear the screen here and try to illustrate the way they do. Okay? Let's say that we're going to draw your y-axes, 3 y-axes here. Okay? You've got a C on each one. So these are your y-axes. So 3 types of behavior that you could have. Okay? Now, these are the critical points. That means that's where the function is, the first derivative is 0, right? The critical points. Okay? They could both be decreasing functions going towards C, and that would be a minimum then, right? Okay? You could be going away from C. That would make that a maximum. Okay? Kind of. On the curve, on the sideways. Okay? Now, okay, and by the way, you could put your y0 anywhere you wanted to here. They put it y0 there, but it would be either place is going to attract it towards C. Okay? If you put this y0 up here or down there, it's going to be repulsed. It's going away from C. Okay? Now, they actually give 4 cases here. It's an attractor in A or repeller in B. Okay? It's semi-stable in both C and D. And here's what we mean there. C, it's repelling above C but attracting below C. And they call that semi-stable. Okay? So if your y0 is up here, it's going to be being repelled. If it was down there, it would be attracted towards C. Okay? The 4th case they give, again, here's your y, here's your C, is that it's decreasing everywhere. So it's attracting towards C from up here and repelling from C if your y0 is down there. Okay? Which means here, wherever your thing would be, it's going to be attracted towards C. Here, no matter where it is, it's going to be repelled from C. Here, it's going to be repelled if it's up here, but attracted if it's down here. Semi-stable. Here, it's going to be attracted if it's from up here, but repelled if it's down here. Again, semi-stable. So the 3 cases, attracting, repelling and semi-stable, but you can have two different cases for the semi-stable. Okay. I hope that's enough. Okay. Okay. Now, for this, the critical, okay. When both arrowheads on either side of the dot labeled C point towards C, all the solution y of x of 1 that start from the initial point x0 or y0 sufficiently near C exhibit the asymptotic behavior. The limit as x approaches infinity of y of x is always towards C. It's always going to C, whether when x is going to infinity, no matter where you're going, it's going towards C. Now, the critical point C is said to be asymptotically stable. This case is asymptotically stable. When x gets very large x, your function, whether you're starting above or below, is coming towards C. Asymptotically stable at C. Okay, that's attractive and attractor. When they're away, that's called unstable. No matter where you are, where it's starting, in large x's, you're diverting, getting further and further from C. That's an unstable. Okay? And that's a repeller. But since C exhibits some characteristics both as attractor or a repeller, that is, solution starting from the initial point sufficiently near C is either attracted from one side or repelled by the other, we say that the critical point is semi-stable. Okay? Here's what you would mean here. If you're starting here, that was heading away for x going y. But if you're starting down here, it's going towards C. So half the time, when it's below C, it's going to be approaching C. Here, the opposite is true. For y is down here, as x gets forward, it's moving away from C. If the y is up here, it's going towards C. So semi-stable, meaning it's stable under one set of conditions, but not under the other. Unstable, stable, stable, unstable. Okay. So that's semi-stable. All right. Now, you don't have a book, so probably, okay. Autonomous differential equations and direction fields. Remember, let's see. You know, more and more I'm thinking, I'm regretting ever starting this section, but I think it really is somewhat important. If all you have is a derivative, dy dx is equal to some function, then whether you can solve it or not, you can at least draw your little arrows in like we did last time. Remember when we did that? Depending on what the function value is at a certain set of coordinates, you can tell if it's what the slope is, plus, minus, you know, which way it's heading. Okay? And in your book, you see these type of things show up here, and sort of a conclusion. They're talking about a translation property, and here's what it says about that. If y of x is a solution of an autonomous differential equation, dy dx is equal to f of y, then y1 of x is equal to y of x minus k, where k is some constant, is also a solution. Okay? Now, what that gives you, okay, and they have some figures, they have some equations, they don't match up, so I'm not going to get into it in too much gory detail, but notice here it's only a function of y. And I think we did one like this last time, whatever your y is, your derivative is always the same as that value of y. There is no x dependence on your derivative, only a y dependence. That's what autonomous means. So they give an example here where all of the slopes of your derivative, all your derivative values are pointing upward, okay, between two values. Here they're horizontal, okay. Now above it, they could be pointing downward, and below it pointing down. So again, this is sort of that case where you have maybe an unstable situation, okay? Well, they give here, if follow the curves, and in between those two critical points, you've got a, and when they say translational thing, then the y of x, y1 of x is equal y of x minus k, where k is some constant. You basically have a curve that's later, I don't know if any of you ever run into anything like that, it's called a logistic curve. It sort of is one of those S kind of curves. And basically, I think we talked about this before, quite often diseases follow that. If there's low disease in the population, there's not much contagion because it's just not there. But once the number of infected people start to increasing, they infect more people, so the rate of infection goes up. But then when you reach near your population, everybody's infected, so no new population. So everybody's been exposed. That's a logistic curve. Now, the only difference here is this has a stable situation at the top coming in that way, and an unstable at the bottom going away. So, but it's just another example of an autonomous differential equation. I think that's more than enough to talk about that. You can do problems 1 or 3, or both if you choose. They've got the graphs there for you. You just have to sort of figure out what's happening there. Then do any of the odds 5 through 11. Then do 13. And then do 15. You can look at the discussion problems if you'd like, okay? I don't think their answers are in the back of the book. Then by the way, those first group were on 2.1.1. They split this into different pieces. 2.1.2, do number 19, then do any of the odds 21 through 27, do 29, and then there's some discussion problems, and you can read through those if you like. And there's some modeling problems. They give you some of those. Population model, terminal velocity, and chemical reactions. 3 different sets of differential equations you could run into. Chemistry person or chemical engineering, that chemistry reaction, chemical reactions might be one down your alley. The others, you choose if any of those make sense for you. Let's move on to 2.2, which is where I wish we had been. I mean, this other stuff is, let's clear the screen here. It's okay, but it's so nebulous and abstract, doesn't feel like differential equations to me. And by the way, that guy who was in my class last term, Cameron, he got an old text from somewhere, maybe he got it off the internet. And the way they approached differential equations was this way. I think that was it, shield, okay? And this is pretty close to how we're going to do it. We're going to do separable equations. That's the first one. H is homogeneous. That's one of the next things we're going to do. I is integration factor. E is I, 1 2, Can't remember E right now. It'll come to me later. L, I think, is linear, and D is can't quite remember that. When we get to it, I think you'll recognize them. We'll start with the S, the separable equations. These, to me, are the most straightforward, the ones you should, and by the way, okay, these are not mutually exclusive. You may have a separable equation that's homogeneous. You may have one that's integrable. You may have one that's linear. And any combination of the several ones, okay? But usually if it's separable, separate. Usually that's what's going to help you the most. So what we call this is solution by integration. Consider the first order differential equation dy dx is equal to some function f of x and y. Okay? Now, that's where we started 1.1 or 2.1 way back. Okay? This is your generic equation. Okay? Now, if that f doesn't depend on y, we earlier called it autonomous if it didn't depend on x. But let's just say it doesn't depend on y, then this changes to dy dx is equal to some g of x alone. And if that's the case, pretty easy to do. Guess what we do? Well, I say, yeah, not yet. Okay? Okay. Here's what we do. We write that as a differential. dy is equal to g of x dx. Okay? Now, it looks like we multiplied both sides of the equation by dx. That's a pretty good tool. We never do that. dy dx is an operator. It's not a quotient. But it still looks like that. Not a bad way to think of it. But just don't. From me. Okay? Now, what do we do here? Integrate both sides of the equation. You got only y's on one side, only x's on the other side. Now, it may be that g of x is not integrable. Oh, you still got the problem there, but at least you know how to approach it. Maybe you're going to do this by numerical methods or something else, okay? Certainly this is just going to give you y, okay? Now, if you have limits, if you don't have limits, it's y plus c, but usually you wait and put the c on that side. So this is going to be y, and that's going to be some function of x. And again, if it's not integrable analytically, you can at least integrate it numerically. Okay, so that's one of the simplest kinds of equations you can run into. Okay, and that will wind up being, this gives you your y, this gives you some g of x, the antiderivative of that, plus some constant function. Okay? Constant, not function. Okay. Where g is the antiderivative, indefinite integral of g of x. Okay? So let's do one. These are so nice. dy dx is equal to 1 plus e to the 2x. Okay? How would you proceed? Yeah, write it as a differential. dy is equal to 1 plus e to the 2x dx. You might, if you want to, put that in parentheses. I don't care. It might help you see it or understand it better. And then you integrate both sides. This will give you y. This gives you, if you integrate one, you get x plus I hear e? Not a bad way to start. Second, integrate e to the 2x, you get e to the 2x over 2. Right? Huh? Okay. And then you would do plus c. Okay? Indefinite integrals, you got to put that plus c somewhere, usually with the x's. Okay, now, if you don't buy that, take a derivative. Derivative of this is dy, all right? Derivative of this is 1. Derivative of this is 1 half e to the 2x times 2, the 2 cancels 1 half, that gives you e to the 2x, that doesn't give you anything, dx. Good deal, that works, right? Okay. All right, here's a definition. Let me clear the writing here. Okay. Equation 1, this one right here, I'm going to clear it in just a second. This is our equation 1, yuck. This is our equation 1, okay? So here's the definition we're going to have for that equation, okay? It's just a special case of when the function f is in normal form, dy dx, well that was the first one we had written there, dy dx is equal to f of xy, okay? Just a special case of that, the special case meaning no y dependence, okay? Now, the second one is, what if this is a function that you can split it into some g of x times h of y? In other words, it's a product of two functions that each has only one dependency, x for one and y to the other. If you've got that, this is what we mean by a separable equation. A first order differential equation of this form, dy dx is equal to g of x times h of y, okay, is said to be separable or to have separable variables. So how would you approach it? Well, write it as a differential first. Dy is equal to, and not just that, at the same time, let's divide both sides by h of y. You can divide that. That is legal. So divide this by h of y. I said y and wrote x, okay? So now we have, here the h of y's go out. So you have dy over h of y is equal to g of x times dx. And you can integrate this and integrate that. And again, usually we put constants on one side, usually with the x's. No real reason to, but yeah, you could, either way would be fine. So, let's do what? Dy dx is equal to y squared x e to the 3x plus 4y. On first glance, does that look separable to you? Does that look like it's a product of functions, x only, y only? Well, the y squared's all right. The x is okay. They're multiplied by each other. But how about that e to the 3x plus 4y? First glance, that doesn't look separable to me. Until I ask you, what are our rules for exponentiation? If you had, let's just take any old base, a to the b plus c, what does that mean? A to the b times a to the c. Isn't that what it means? If you have the same base, different exponents, keep the base, add the, and they're multiplied, keep the base, add the exponents. So let's do the same thing here. This could be written as y squared x. What would that be? E to the 3x e to the 4y. Now they're separable, right? So let's write it as dy and a dx over here. Let's divide both sides by y squared e to the 4y. And you get rid of that, and you get rid of that. So now we have the integral of dy over y squared e to the 4y is equal to x e to the 3x dx. And take the integral of both sides. I should have waited to do the integral of both sides. Now, I think I'm willing to make an attempt on the right-hand side that looks like integration by parts might work. I believe it will. I don't think it'll take too many steps to get there, but I think it'll work. Ooh, but this left-hand side is really not very pleasant looking at all. I'm not sure I know how to integrate that one. Okay? Oh, maybe. Wait a minute. We could write that also as the integral of y to the minus 2 e to the minus 4y dy. At least looks a little better, but it still would take integration by parts. The trouble is this never gets any easier, because when you take derivative of this, it gets more complicated. Now you take the integral of that and differentiate that, and that would do okay up to a point until you get a log y, and then I don't know what you can do from there, okay? So I'm not absolutely certain that is integrable. Let's see what they say. Maybe they see something I don't, okay? Oh, they were asking me to, were they? They were just saying, yeah, you can separate them. Notice they didn't say how you integrate once they're separated, okay? The second equation, there's no way of expressing, oh wait, no, I'm sorry. So that is separable. No guarantee it's integrable, but it is separable. Okay. Now, let's look at another one. Let me go on and clear this. Okay, this one is dy dx is equal to y plus sine x. Separable? Remember, to be separable, a first-order differential equation of the form dy dx is equal to a product of two functions, each one of a separate variable. This is a sum of two functions. Nothing, you can't separate that as a product at all. Not separable. Okay? Don't even try. Okay? Not separable. We'll have to wait until a later section to come up with something. That's not separable, go to something else. This won't be homogeneous. I think an integrating factor may be our solution to it. We're not there yet. We'll wait till we get there. If we think about it, we'll come back and look at it. Okay? Now, let's look at something else here. Observe. Okay, we've already done that. Okay. They make an observation here which feels like they're pulling it right out of some place we won't mention. And you want to say, so, or what, or whatever. Observe that when dividing the function h of y, now this is going back to what we were doing before, when you have, and this is the one not separable, so I'm going to get rid of it. Go back to what we had before. Those that are separable. And this would be dy dx is equal to some g of x, h of y. Okay. We can write a separable equation as, now, just like we did before, we're going to write it in differential form and also divide both sides by h of y. Okay? These go out, and shouldn't do it this way, but I'm going to wipe out the dx and put it over here. Okay? Now here's what they say. If 1 over h of y is a function of y alone, then that also corresponds to a function p of y, where p of y is 1 over h of y. Only a y dependence, but now it's not in the derivative again. Remember, that's what I did when I wrote that y, 1 over y squared is y to the minus 2, and wrote e to the 4y as e to the minus 4y. I wrote it as a function that you can put up top, for whatever reason that is. So now we have dy, and they're writing dy dx, and I'm not really sure why. I'm going to skip that step, is equal to g of x dx. Okay? Now we integrate both sides. Yeah, it's a p. The given here is that 1 over h of y is now some other function, p of y. You moved it into the numerator. It's the same function, it's just without a radical form, a rational expression. You've written it as exponential or something. You've written it just as some other function of y that is the same value. Okay? So why would you do that? Okay? Well, do you remember if you look at this carefully, look at their equation 3, those who have books, okay? And I think, why in the world have they introduced something so bizarre here and then immediately going to turn around and rewrite it as something that I've got right here? Why didn't they just write this? Why have that intermediate step that really does not clarify anything? All it seems to me to do is muddy the waters, okay? And I see no reason for doing that. So I'll go right to that step, okay? And then we'll say that this one here, and then they choose h, and I'm not sure why, but the antiderivative of p of y, if you can do it, is h of y, and the antiderivative of g of x would be capital G of x, and then you always have the constant. Okay? So there's your solution. Okay? If you can do it, where h of y is the antiderivative of p of y, but p of y, remember, was the reciprocal of y, of h of y, so I don't know why they go to all this trouble. Now, let's look at when they have these little bars, they're sort of starting something new. Equation 4, which is the one we just did here, basically, indicates the procedure for solving separable equations. A one-parameter family of solutions, usually given implicitly, is obtained by integrating both sides of p of y, d dy equal g of x dx, and integrate both sides with respect to the thing. Note, there is no need to use two constants in the integration of a separable equation, because if you write them, then you can just subtract C1 from the other side and make it C, okay? So there's no reason to do but one. All right, all the blah, 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 let's actually do an example, okay? And I think you'll find these they come close to being fun, okay? They're usually pretty reasonable. Let's solve this one. 1 plus x dy, now they've already written this one in differential form, minus y dx is equal to 0. Now later we will talk about functions that are written in this form, and we'll deal with them in a different way too, but here this one is clearly separable. What would be your first step? It may not be clearly separable. What would you do? Say that again. You may have said it right, I just don't hear well. Okay. Okay, yeah, let's move to the other side. Yeah, we'll have 1 plus x dy is equal to y dx. Add a y dx to both sides. Okay? Now we got, but we've still got x's and y's mixed, but what were you suggesting next? Divide both sides by 1 plus x. So let's do that. But at the same time, let's divide both sides by y. Why not? Okay? Now over here, your 1 plus x's go out. Over here, your y's go out because they've been dating. No, never mind. Okay, and what does this give you? This gives you dy over y is equal to dx over 1 plus x. Ha! I think I can integrate both of those. Can't we? What would the left-hand side be? Say again? Say again? Yes, ln of y is equal to, look at that, ln of 1 plus x plus c. Except I really don't want to put plus c this time. I want a different constant. What constant might I want? Okay, let's see. Ooh. Do the eraser and it doesn't show up. Okay. How about let's do an LC, log of c. Isn't that a constant? Okay. Now why would I do that? Who knows? Okay. Now, here's why I would do it. What's the sum of two logs? Say again? A little louder? Okay. Let's do ln A plus ln B. Now notice these are same bases. Isn't that the same as the log of AB? Isn't that one of the properties of logarithms? The log of a product is the sum of the logs. Right? You buy that. See, y'all will buy anything, won't you? Okay, now y'all must be rich. No. You youngsters don't remember slide rules. You probably don't even know what a slide rule is, do you? Okay? But what a slide rule was what we used to calculate before they had calculators. Hey, you got another presentation today? No, you're in the right, but I go till 3:15, but but I didn't know you were going to be speaking because I had plans this afternoon. I'll try to come up. This is differential equations, and we get through at 3:15, and then y'all start at 3:30. Okay. Dr. Bryant's right there, so you can go on in. Okay. Yeah. Good deal. Y'all heard him a couple weeks ago. Yeah. Yeah. Okay, good deal. Okay, so with this in mind, what does this become? log y is equal to, here's the sum of two logs, that would be c times, I'm sorry, boop, 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 boop. Okay. This would be the log of the product of those two, c times 1 plus x. Right? Now what can we do? See it? Does that make sense? Now what can we do? You got logs on both sides. What if you don't like messing with logs? What can undo a log? Say again? You say an axe will take it apart? No. A chainsaw? No, that's not the log we're talking about. What function undoes the ln function? The exponentiation function. Let's take an e of both sides. E this, e that. The e and the ln's undo each other. Yes? Yeah, 257?
Yeah, that's our lab, right? Physics lab.
Oh, you mean the one down the hall, 203.
Yeah, I like to see what equipment is there so I know what I don't have to bring.
Right. I don't have a key to it, but you know Jamie Glass downstairs?
Yeah.
Okay, go see if I know she has a key. If she's in, she can, unlock it for you. Yeah, or campus police can too. But I don't have a key to it yet. Well, I need to do a key request. I meant to do that a couple weeks ago. I forgot. Okay, no problem. Okay. Okay. So there you have a y. And what do you have here? You have c times 1 plus x. Hey, there's a one parameter solution. Okay? Y is equal to c times 1 plus x. Okay? Now, let's see if I have, okay. Yeah, all right. Let's see what they did. Ah, there it has it. Y is equal to c times 1 plus x. In blue, it must be okay. Now, they have a lot of little stinky steps in there, and they are important. Actually here, this should be absolute value of y, this should be absolute value of x, and of course that c has to be positive, okay? But you know what? As long as all your things fit, it comes right out being this, okay? All right, make sense? Oh, sad. They interrupted us, didn't they? That wasn't fair, okay? All right, what we'll do here, don't you find this so much easier, or so much more fun than the previous section? It's just a lot of blah, 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 okay? Okay, we'll start at the top of that page next time. And homework exercises, I think you can do any of the odds 1 through 7. No, I'm sorry. 1 through... We've only done one example. I know you can do all of the odds 1 through 7. 9 is a little more, you can still do 9. I think you can do 11. I think you can do 13, 15, 17 might take a bit more work, okay? So let's hold off 17 and we'll pick up there. So try to do any of the odds 1 through 15. I think those are all fairly reasonably doable. Okay? All right. Good deal. And I apologize to the people who got here early. I think that was Jonathan. Okay. I have your test within probably a half hour, 45 minutes of being ready. I've got it all typed in, but I just didn't get a chance to. Actually, I had my work study student type it in, but I've got to go and check it and make sure he didn't drop a sign somewhere and smooth it up, clean it up, because I think when he typed it in, it went more than 2 pages. I don't want to give you a test more than 2 pages, so I'm probably going to have to take out a problem. Sorry about that, and we'll go from there, okay? So anyway, we'll see you Monday. Have a good weekend, and we'll catch you then. And if y'all can, well, I don't know. Did he say he was giving a lecture, or is he just checking out equipment?
No, he's doing.
He is doing, okay. So much to do. I want to come here, but I'm afraid